Today we're going to finish up chapter 8. Chapter 8. That means we only have one more chapter to go, and that's chapter 10. So we're at the end of the line here. Okay. So far, what have we done? We've looked at integrals that, no, so far, we looked at integrals whose domain of integration, the bounds, closed interval from, remember that those are the ones from A to B, are finite. So we have to start from A to part B. So that's the domain. This also, the range of the integrand, the function inside there, is also finite. So far we're looking at finite functions. So the integral from A to B, that's bounded, and the function itself is finite. So it'll come up with a actual value. We'll get a term, a solution to this. These are what we'll call proper integrals. The domain's finite and the range is finite. Now, we will look at improper integrals. Basically, we're looking at the ones that are infinite. So we can look at any function, say 1 over x. It has a horizontal asymptote at 0. So the graph will never cross the x-axis. And it has a vertical asymptote also at 0. Again, it'll never have a y-intercept. So if we're looking at, we have A and B here. If we were looking at this part, it's finite and we can find the area under the curve. What if we're looking at from 0 to A? Or from B to infinity? These areas. Since they never end, this is going to infinity. The function here is going to infinity. So basically, as I said here, the domain is finite, the range is finite. The domain is infinite. And the range is infinite. Those we call improper fractions. But here's the cool thing about it is, if we were looking at something like this, we think that if we look at the integral, the area of this thing would go on for infinity, would never have an end of it. But what we're looking at here, though, is we will have some sort a limit that we'll get to. So it will have an integral. So the example that we're going to look at first is, let's look at our function f of x equals e to the power negative x over 2. We can look at all these ways here. So now remember, this is an exponential function. This is e to the power x. Since our x values, whatever I choose here, I divide it by 2, the e values will still keep on getting strong, higher and higher and higher. But as x goes to infinity, this function will go to infinity. So we'll have a function that pretty much will look like this for us. This is that one. This is e to the x over 2. From algebra, if your exponent is negative, it's a decreasing function. If your exponent is positive, it's an increasing function. From algebra. So we're looking at from this realm. We're looking at from some value b all the way to infinity. And then we'll also look at from 0 to b. All right, so let's look at this first part. From 0 to b, whatever value that is, we have our function e to the power negative x over 2. The integral of that is the derivative of this would be negative 1/2. So that means we have to have a negative 2 in front here because it cancels out. So we have to have a negative 2 out in front here. And the integral of e is e to the x over 2. Okay, so take the constant out. We have e to the power negative b over 2 minus e to the power 0, which is negative 2 e to the power negative b over 2 plus this becomes 1. So that's our integral. Now, again, as b goes to infinity, this goes to 0. So all we have left is 2. So again, we will have a finite limit as we start looking at these. So as we said here, we had from 0 to b of our function is negative 2e to negative x over 2 plus 2 and then negative b. But if we take the limit as b goes to infinity, this one goes to 0. So negative 2 times 0, so it's just 2. right? So no matter what b is, as we go towards infinity, that's what's going to happen. So we're saying we're going from 0 to b, that goes 0 to infinity, as b goes to infinity. So we will have as the limit as b goes to infinity. Right? So this is the formula we'll be using. So let's define this. Improper integral is an integral with infinite limits of integration. Okay. So that, when we talk about improper integrals, that's what we're looking at. Three types, or three forms. For all of these, our function is continuous, continuous and differentiable on an interval. It's the interval that's the question. So the first one, if our bounds of integration is from some value to infinity, then we get f of x dx is equal to the limit as b goes to infinity from a to b. So there's our first one. That's if we're going from some value to infinity. Let's say we go from negative infinity to some value. Because we're looking at a to b. If this is true, then we'll go from negative infinity to b of our function equals the limit as a goes to negative infinity, because that's where we want to go to, of a to b. Because that's what we want to get to. Remember, our first term is a. And then the last one, 3, is we're going to take the end bounds from negative infinity to positive infinity. It's an infinite sequence. So we're going from negative infinity to positive infinity of some function. When this happens, we have to break them up into two parts. So we'll have some intermediary point C, and it's irrelevant to which value C you're picking. So we're going to do it in two parts, from negative infinity. So we're going to make it into both of these, from negative infinity to B, and then from A to infinity. Right, so let's look at an example. Nemo. Stop. Oh, nice. We have to discuss the concepts of convergence versus divergence. So in our previous examples, if the limit exists and is some number. It is finite. Nemo, stop. And we say the improper integral converges. It converges to a point, to a value. Is the finite number that you came to. So that's if the limit exists, one of those examples we did in the past. If the limit does not exist, in other words, it fails, then we say the limit diverges. I mean, not the limit, but the improper integral diverges. All right, so let's look at an example here. Example 1. Or my example sheets. Oh, there. Okay, so here's our example. Is the area under the curve y equals ln x over x squared from 1 to x infinity finite? If so, what's the value? From x equals 1 to x equals infinity. Is it finite? In other words, does it converge? So what are we looking for here? We're going from our conditions. These are our 3 conditions. So we're going to look at the first one, going from some number 1 to infinity. No, this is going from 1 to b. All right, so we got first. We have ln x over x squared dx is ln x times 1 over x squared. So we're going to have to use integration by parts because there's no integrals that'll fix this. So remember the ln x, yeah, because then the derivative of that is okay. Yeah, so then du will be the dx over x squared. Du is this 1 over Remember, I need to have the U, V, du, dv. So this will be dv. So my u is ln x. My dv is the derivative. It's 1 over x squared. Okay. So then the derivative of u du is 1 over x dx. So it's dx over x. And the integral of this one is x to the negative 2, add 1. So it's negative 1 over x. Okay, right. So that's how we break this one up to pieces. Remember what it was as well. So it was uv minus the integral of v du. So u is ln x times v, which is negative 1 over x, minus the integral from 1 to some value b. V is negative 1 over x. Du is 1 over x. It has to have a dx for the whole function. Okay, so this is negative ln x over x. The integral of this so the derivative, this is now going to be negative 1 over x squared. So the integral of that is 1 over x. From 1 to b. So we have negative ln b over d minus 1 over b minus ln 1 over 1 minus 1 over 1. This goes to 0. For ln b over b minus 1 over b, negative plus 1. Okay, where's my previous sheet? Then we have to take the limit as b goes to infinity. So now we take the limit as b goes to infinity. This function. Ln b negative over b, this one goes to infinity, so that one goes to 0. That one goes to 0. Or as b goes to infinity, we just have 1. So that's our limit. So it converges to 1. Okay, do the same thing next one. Dx over 1 plus x squared. integral from negative infinity to infinity remember, condition 3, negative infinity, infinity, we're going to break it into 2 pieces. So we have negative infinity to infinity dx over 1 plus x squared. Okay, so you pick any value of c you want. So in this case, let's pick c to be 0. Let's look at both of these since we'll treat them both separately. But this first part will be done this way. So from A to B, and then this part will be also from A to B. So use our properties. So this one here becomes the limit as we change for A. A goes to negative infinity. The limit as A goes to negative infinity. The integral of this 1 over 1 over x squared is inverse tangent from A to B. Well, this one's going to 0. And A is going to negative infinity. So at this one, we have inverse tangent of 0 minus inverse tangent of A sine inverse tangent at 0 is 0. Inverse, where is it equal to 0? Inverse is cosine over sine, so it's at pi over 2. We're doing inverse. And we're going to negative infinity. So as A goes to infinity, our limit converges to pi over 2. That's the first one. Do the same thing for the other one now. This is the first part. This is the second part. So now we're going from 0 to infinity. And that's going to be from example 2. Or no. That's condition 1 for the definition. Going from 0 to b, the limit. The limit as b approaches positive infinity, we're going from 0 to b, dx 1 plus x squared. The integral of this as b goes to positive infinity is inverse tangent of x from 0 to b. As b heads to infinity, we have tangent inverse of b minus tangent inverse of 0. The 0 goes to 0. As b goes to infinity, this inverse tangent goes to pi over 2 minus 0, which is pi over 2. Nemo back. So that tells us we take a plus b, we get pi over 2 plus pi over 2, we get pi. So our function converges to pi. Right? Yeah, this is a little bit more because the formulas are not that straightforward. Next, let's look at this type of function. An exponential function raised to some power p. So how would we approach this from now? Let me see, that one is example 3. So we're looking at this type of integral. The function rho of x is the boundary between convergent and divergent improper integrals, so the integral 1 over x to the power p. This one shows how the improper integrals converges if p is greater than 1 and diverges if it's, sorry, as we just seen, if it converges if our exponent is greater than 1 and diverges if it's less than 1 or equal to 1. Let's look at that 2 ways. Converges if p is greater than 1. That was it, yeah. And diverges if p is less than or equal to 1. We're looking at the function 1 over x to the p, or x to the negative p. All right, what happens, what this function is going to look like is, no matter what x we pick, let's say it's 2, so 1/2 to the power p. Now, as p gets larger and larger and larger, this bottom number gets bigger and bigger and bigger. And then what happens there is it eventually goes down to some value. Because when p is 0, it's 1 over 1. It's 1. When p is -1, negative, so it's at 2. So this graph is a decreasing function, which is why it converges. Because eventually we're saying it converges because it's getting closer, closer, closer to this line here. Now, if it's negative, if P is negative, and negative went to the positive, if P is negative, it goes up on top. So if we have this, then it becomes x to the P. As P gets larger, this function gets larger, 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 and larger, and it diverges to infinity. So that is what's happening with that in a nutshell. So let's see how we would approach this in this equation. So the question is asking us, for what values does P converge when the integral, what is the value if it converges, or when it converges? We don't want P to be 0 or 1, because if it's 0, that means the bottom is 1, we just have dx, which is just x, which becomes a diagonal line. We don't want it to be 1, because then it's just x, and the integral there is just be the ln. So let's look for anything else. So we're going to go from 1 to some value p, because we're going to infinity, so we're going to b. The integral of this is negative x to the p, so negative p plus 1 over negative p plus 1. One over negative p plus 1, x to the negative p plus 1. So it's b negative p plus 1 minus 1 negative p plus 1. So it doesn't matter what the power is, it's still going to be 1. So then we have 1 over b p plus 1, or p minus 1 now. For any value p greater than 1, yeah, so it can't be 0 down here, so it can't be undefined. So as p gets larger, this will go to 0. So, and this, as p gets larger, this goes to 0 as well. So if we look at this, as b goes to infinity of this function, one over b negative p plus 1 or minus 1. So if our p-value's positive, then this number gets bigger and bigger and bigger. It goes to 0. So the function goes to 0. it converges. If P is less than 1, this becomes positive. So 1. So this gets bigger and bigger and bigger. I mean, it gets smaller and smaller, actually. As B goes to infinity, remember what P is. P is less than 1, so it's negative. Yeah, okay, that's what it is. P goes over here, it becomes larger and larger and larger, minus 1. This one grows faster than this one goes smaller. Yeah, but that's if P is negative, say we have 1 over B to the negative P, which is B to the P. So as P gets larger and larger and larger, this one goes to infinity. So this one goes to infinity because it's an exponent. This one just gradually it goes to 0 slowly. So that goes faster. Yeah, so that's what we're looking for. That's what we're trying to find there is with this function, we get the integral, take the limit as our value goes to infinity, because we're actually going to end up with no P's a single value. No, yeah. So if P is 3, negative 3, so it's be 4. But then as B goes to infinity, this one it'll be B to negative. So yeah, that's right. Now here's what's happening. Let's say P is negative 3. P is a single value. B goes to infinity. So 1 over negative of negative 3 plus 1. 1 over B negative 3 plus 1 minus 1. So this becomes 1/4. That's going to always stay 1/4. This becomes negative 2, so it becomes B squared minus 1. Now, as B goes to infinity, this one just stays 4 divided by 4. This one goes to infinity, minus 1 over 4, so it still goes to infinity. Okay. But we have to remember that the B value is what changes to infinity. P, once you pick that, it's one single value and it stays fixed. I was changing them both going to infinity. Okay. Integrands with vertical asymptotes. Now, these are our functions. A vertical asymptote is when the denominator equals 0. It makes the function undefined. So, for example, the vertical asymptote here is at x equals 0. And so this is what we're going to look at. So if we look at this function here, 1 over x, we have that function. We're only going to take from 0 to infinity. So that's our, we have two values, a and b. from 0 to A, we have, it never touches, never crosses x-axis, so we're looking for this area. From B to infinity, we're looking for this area, and it gets closer to the x-axis. And then we have this one, which is a finite set. All right, so let's look at from 0 to A to some value B. So if we look from A to B, that would be ln x and it can't be 1. The ln function looks like this. So we can't have 1 be 0. Yeah, let's go from 1 to 4. Or 1 to E. Makes it easier. So ln E minus ln 1. So that's what the function would be. So we're still going to look at the integrals. Let's see where are. Yeah, so we have the sheets I'll upload with these notes as well. These integrands with vertical asymptotes. So here we have now the definitions for these, because now we have 3 other functions we have to worry about. Integrals are functions that become infinite at a point within the interval of integration are improper integrals of type 2. This is where you have an vertical asymptote. Again, integrals of functions that become infinite at a point within the interval of integration. So somewhere between A and B, there's a point C where it goes to infinity. These are improper integrals of type 2. So if fx, they're all continuous, except this last one, because going from our end bounds, and we have to divide them into 2 points. So if it's continuous on A and B, cannot equal A, can equal B, and discontinuous at A, that's why it's not included, then this limit, C as approaches A from the left, or from the right, is this function. We'll use this equation. So if we have our closed interval closed to open, open to closed, then we have to use this one. We're going from C equals A, or go to A to the positive. Now, if we're going from A to B, and B is the discontinuous point of discontinuity, then we're looking at B from the left, because we're approaching this way. We're approaching it this way. So if it's discontinuous at some point C, so we have A to C, C to B. In each case, if limit exists, it's finite, the improper integrand converges to a limit value. The value is a point. If it doesn't, it diverges. So it's the same thing we did with the first part. All right, so let's look at an example here. Example 4. Investigate the integral. Investigate the integral here. Check the convergence. Okay, that's pretty straightforward. Get another sheet. Example 4. So we're looking at the from 0 to 1 over 1 minus x dx. This is continuous on 0, and it can't go to 1. So let's first determine from our, where's that? That's yours. So bracket there. So we're looking at type B and number 2. And it's discontinuous at the endpoint. At the endpoint, so we'll have to use this formula. We're going to use the limit as C approaches B from the left, A to C f of x dx. That's what we'll be using. So let's find the limit as C goes to some value 1 from the left. Oh, what do we use there? C of 1 over 1 minus x dx, which is equal to the limit as C approaches 1 . The integral of this function, we need a negative. So it should be negative ln, the absolute value of 1 minus x. From 0 to b. C. But that's not in our inverse. So this one becomes negative ln 1 minus c minus ln 1 minus 0. C is equal to, it goes to 1 from the left. Ln 1 minus c. This becomes a plus ln 1. This goes to 0. So as C goes to 1 from the left, okay, as it goes to 1 from the left, it gets closer, closer, closer to 1. So 1 minus 1 is 0. Remember, the ln function looks like that. So as this value here, when it gets closer to 1, it gets closer to 0. It goes to negative infinity. So it goes to negative infinity. So it goes to positive infinity. All right, let's look at. Yeah, so once you understand how to apply those functions, let's look at 5. Our not 5, not 5. Okay, evaluate this integral from 0 to 3. Example 5. From 0 to 3 dx x minus 1 to the 2/3 power. We're given 2/3. So which one doesn't satisfy? We have a vertical asymptote at 1. And that's intermediary point here. So that means f of x is discontinuous at some point C inside our bounds. So we got to use this one. We go from 0 to 1, 1 to 3. Because that's our asymptote. So we're looking at the limit as our value b goes to 1 from the left. I jumped too far. So let's first set this thing up. From 0 to 1. From 1 to 3. All right, so this first part. Yeah, let's do both together. So this is from 0 to 1 dx x minus 1 2/3. And this one is from 1 to 3 dx x minus 1 2/3 equals. So I got to do both of these separately. So this one, according to our formulas, as b approaches 1 from the left of our integral from 0 to b, dx x minus 1 2/3. And this one's going to be the limit as b approaches 1 from the right. Now, why is this? Because if we look at this, we're going from 0 now we're going from 0 to 1 and from 1 to 3. So for this one, we have to come from the left, and from this one, we have to come from the right. Let's finish this one. Integral of this one. The integral of this one is going to be up, so it's negative 2/3. Add 1, So it's x minus 1 to the 1/3 over 1/3. Get rid of it. The integral of this one is going to be x minus 1 to the 1/3 over 1/3 from 1 to 3. So that one becomes b minus 1 to the 1/3. This one becomes a 3 coefficient. Minus 3, 0, minus 1 to the 1/3. So as b goes to 1, this one goes to 0. This one becomes -1 to anything is still -1. -1 is +3. So that one's 3. And so I have the limit. Three b minus 1 to the 1/3. Minus 3, 1 minus 1 to the 1/3. One minus 1 goes to 0. 3 times 2 to the 1/3. 3 cube root of 2. So our solution then becomes 3 plus 3 cube root of 2. That was a pretty interesting one. Where's my example sheet? Okay. Now we're going to look at, well, improper integrals with computer algebra systems. Well, I'm not worried about that because I'm not going to use those. We have calculators that do more than the systems do. So, tests for convergence and divergence. When we cannot evaluate the improper integral directly, we try to determine whether it converges or diverges. If the integral diverges, that's the end of the story. In other words, it goes to infinity and nothing we do about it. If it converges, we can use numerical methods to approximate the value. So the principle tests the convergence or divergence of a direct comparison test and the limit comparison test. And here we are. The direct comparison test. Let f and g be continuous on some interval from a to infinity, and f is between 0 and the second function g of x for all the x's greater than a. in order for everything greater than from a to infinity. Then we have if a to infinity g of x converges, then f of x converges. If f of x diverges, then g of x diverges. Remember, what we have is this. If this one diverges, if it goes to infinity, this one's larger, it also has to go to infinity. So it diverges. If this one diverges, this one diverges. So if this one becomes a number, that means this range is finite. So this one has to equal some number. So it converges. That's what that comparison test says. All right, so let's look at example 6. Does the integral e to the negative x squared converge from 1 to infinity? Example 6. From 1 to infinity, e to the power negative x squares. Does it converge? Remember, we can use the comparison test. So we have f of x, g of x. So we're saying if it converges, we have to find a value g of x that we know that converges, but it's larger than this one. Okay, since this is e to the x squared, how about just e to the x? Because remember, the smaller the denominator, the larger the fraction. So when I square x, it's going to be a much bigger equation on the bottom. So there. Now we have to test, does this converge? It's getting closer and closer to 0. So we can't actually, yes, we can say that this function converges because this one converges. Let me use that one. So let's look at this. We have, well, we read the integrals from 1 to infinity of 1 over e to the x squared dx, 1 over e to the x dx. This one becomes e to the negative x. The integral of this one becomes negative e to the x. So this is negative e to the x from 1 to infinity, or if 1 to some value b. E to the x. The derivative of, so I have to have a negative out in front. Yeah, so we have to have a negative there. So it comes negative e to the x, so it's negative b plus e to the, well, it's a -1. There's a negative e. So that's -1 over e to the b plus 1 over e. That's less than 1 over e, which is 1 over 2.18. So it's a finite, so it converges. So since this one converges, this one converges. So what we'd have to do is figure this out. 1 to b of e to the negative x squared dx. That we'd have to figure this out. But we know it converges because it's between 0 and this value. And we know this one converges. It's a finite number. Okay, that'll work. Okay, let's look at example 7. These examples illustrate how to use theorem 2. That's the direct comparison test. Oh. Okay, look at this one. What was example 7 in my sheet? There we go. These examples illustrate how to use theorem 2. Okay, so let's see this. A. Sine squared x over x squared dx. So just remember we're on the interval 1 to infinity. And as x goes to infinity, this one diverges to 0. So since it's bounded by that, it converges. Because this function here, as x goes to infinity, this function goes to 0. So we're saying that this function also converges, goes to 0. Or the integral of it does. The next one. From 1 to infinity, x squared minus 0.1 we're on the interval 1 to infinity. 1 over x squared. As x gets larger, this one's smaller than this one. Okay, so we know that this one is larger than this one because this one grows much faster than this. So this is what happens with that. Not x greater than or 0. So let's try that. This one becomes ln x. Yeah, so this one, 1 over x, is bigger than this one because square root of x squared is x minus. So this is a smaller function. This is smaller. This is larger. So it makes the fraction smaller. So since this one diverges, it goes to infinity. Then this one is larger than it, so it also diverges. Let's look at example 8. Or do we have an example 8? The limit comparison test, yes. If the positive function f of x and g of x functions are continuous on this interval, and if the quotient f of x over g of x is x goes to infinity equals some limit, and it's a finite limit, then f of x and g of x either both converge or both diverge. Okay. Although the hyperbolas of two functions from a to infinity may both converge, this does not mean that the integrals necessarily have the same values. But if they're both either going to converge or they're both going to diverge. So example 8. This is that other one. Plus x squared. Converges by comparison with one over x squared. Okay. That example sheet says. So the limit comparison test. The limit comparison test does this. So we have to have an f of x and g of x. So the smaller one. they cannot be negative because x squared, even if negative isn't there, so it'll always be positive. It's continuous on the domain from 0. X cannot be 0 here. So on this domain, it's continuous. Those are the two conditions. So it says if the positive functions f and g are continuous, they're both positive, and they're continuous on this domain. Now, let's look at this. If this equals limit, and the limit is finite, then we're both going to converge or diverge. So let's start from here. So we have the limit as x approaches infinity of 1 over x squared, 1 over 1 plus x squared. Plus x squared over x squared. Reducing two parts. Limit as x approaches infinity of 1 over x squared, plus the limit as x approaches infinity of x squared over x squared. 1 over x squared as x goes to infinity goes to 0. This one becomes 1. So L is 1. Okay, which is, it satisfies this condition. So we have to compare we did this one already. We know that this one converges. So this one is 1 to infinity. So I add 1 there, add 1 there. So x to the power -1 from 1 to infinity. -1 over x. So this is 1 over infinity minus -1 over 1. This one goes to 0, negative, positive 1. This one converges. So this one converges. By theorem 6. By theorem 3. Either they both converge or they both diverge. So they both converge. So if they both converge, what value does it converge to? So the integral of 1 to infinity of 1 plus x squared the limit as our b value goes to infinity from 1 to b of our function. equals the limit as b goes to infinity. The integral of this 1 over 1 plus x squared is inverse tangent x, 1 to b. Inverse tangent of b minus the inverse tangent of 1. Now, as b goes to infinity, inverse tangent, as x tangent goes to infinity, inverse tangent goes to infinity, and inverse tangent goes to infinity at pi over 2. Graph the inverse tangent looks like this. It's repetitive sequence. Minus, where does the inverse tangent equal 1? That's square root of 2 over 2. The tangent, inverse tangent equals 1. Sine, so it equals at pi over 4. It's a 45-degree angle. So 2 over that's 2 radical 4 over. So that's the value it converges to. Yeah, review, because remember, the inverse tangent of some value here, this is infinity. So at what point does the inverse tangent go to infinity? It goes to infinity at pi over 2. So where does the inverse tangent go to 1? Tangent is 1 when it's square root of 2 over 2. Sine and cosine both square root of 2 over 2 square over 2. And that occurs at pi over 4. This is 45-degree angles. So again, review those, makes it much easier to do. One more. Find that one. Investigate the convergence of this function. 1 minus e to the negative x over x dx. So according to theorem 3, as x approaches infinity of f of x over g of x. So we have to find a comparison. As the theorem said, limit comparison. Oh, there's it. So I have to compare it to 1 over x. This is d. And that's my f of x. So the limit as x approaches that, that 1 minus e to the negative x over x over 1 over x. So take the top one, leave it alone. And flip the bottom. We could have just multiplied the top and bottom by the LCD. And we'd end up with just that part. So as x goes to infinity, as x goes to infinity, this one goes to infinity, so it goes. So the limit of 1 is 1. It's positive. It's finite. Let's see what that's. Either both diverge. We have this. It's a limit. It's finite. It's between 0 and infinity. Either both converge or both diverge. What happens at 1 to infinity of 1 over x? So this one becomes ln x, ln infinity minus ln 1. It diverges. So 1 minus e to the negative x over x diverges. Yes. Okay. Well, that does it for that section. That does it for that chapter, actually. We're done with chapter 4 now. And we start chapter 5 and see how far we get this week and a little bit next week. All right. Have a great day, everybody.